Okay, so what I want to go over today is the mechanism of the NBS bromination. NBS, remember, is N-bromosuccinimide, which is the molecule you see on the top left-hand side of the screen here. And when you react that with a little bit of HBr, it will turn into succinimide, which is the imide on the right, where the bromine has been replaced with a hydrogen, and it generates Br2. And the whole trick to this reaction is that what you're trying to do is you're trying to generate Br2 at an incredibly low concentration, one molecule at a time, if you want to think about it that way. And one of the things you have to think about when you're doing this reaction is how is this going to happen? How is it that you get Br2 when you're using HBr in NBS? And so here's one thing to think about. So remember, HBr is a molecule where, if you think about the dipole moment there, it's going to be polarized towards the bromine, and there's your source of Br minus. That means that the NBS must somehow be a source of Br plus. And so if we can somehow get Br minus and Br plus to come together with each other, we will generate the Br2 we're looking for to do the reaction. And so that's the trick with the NBS mechanism. That's what we're trying to think about here. So how do we go about doing this? So you take your NBS and a little bit of acid. NBS it's a white, yellowish kind of powder, so it's nice to work with in the lab because it's a solid. And you don't actually have to add any HBr usually to this reaction. You can, and sometimes protocol calls for it, but often there's enough trace amounts of HBr in the jar. Even though it looks like it's a dry powder, there's enough trace HBr in there that once you put it in the solvent, it will protonate and get the reaction going. And so what gets protonated here? Well, so if you think about it, in the imide here, there is a lone pair of electrons on that nitrogen. And so that lone pair of electrons on the nitrogen is going to be in resonance delocalization with the carbonyl. Actually, with either one of the carbonyls. So there's two different ways to resonance delocalize the lone pair on the nitrogen. So I'm going to pick a way here. And I'm going to think about the electrons delocalizing up onto the top oxygen, which makes it more electron rich, which makes it more nucleophilic or Lewis basic, which means I'm going to pick up a proton onto that oxygen, and that's how I'll start the reaction. You've seen that a bunch of times in class where you get the lone pair of electrons, protonate the lone pair of electrons with a proton, and you're off to the races. Okay, so you protonate that oxygen and you make the oxonium ion. And that's going to make the molecule want to resonance delocalize to stabilize that plus charge. And when it does that, the electrons in the carbonyl oxygen are going to resonate out of the oxygen. And what that's going to do is that's going to put a plus charge on what was the carbonyl carbon. That, of course, is now a plus charge right next door to the nitrogen with a lone pair. And so the lone pair and the nitrogen are going to want to come over and delocalize to further stabilize that plus charge. And so when the lone pair and the nitrogen come over, you make a double bond between the carbon and the nitrogen, and that leaves a plus charge on the nitrogen. So that's an iminium ion. And bingo, that is where you get to understand why and how this reaction generates Br plus to react with your Br minus to make Br2. Because if you think about it, so now in this molecule here, the nitrogen of the iminium ion being plus charged is really going to polarize the electrons in the nitrogen-bromine bond towards the nitrogen. Normally, I would think of the electrons in a nitrogen-bromine bond to be polarized towards the bromine. Since bromine is on the far right side of the periodic table, it's a halogen. However, this is not a nitrogen, this is an iminium nitrogen, which has a plus charge, and that means the polarization is going to go from the bromine back onto the nitrogen. Almost all nitrogen-containing chemistry can be explained by focusing on the fact that the nitrogen wants its lone pair of electrons back. So now, with the iminium ion polarizing to pull the electrons from the bromine back onto the nitrogen, that generates a Br+. And if that generates a Br+, that means you've got a way of making Br2 by taking one of your Br minuses, which has been floating around in the beaker ever since step number 1. And so a Br minus hits the B+ of the iminium ion, gives the nitrogen its lone pair of electrons back, and puts it onto nitrogen as a lone pair, and therefore generating Br2 as your molecule which floats off into the beaker. Okay, and the whole purpose of it was to do just that, to have Br2 generated one molecule at a time, really, really low concentrations in the beaker. Now, if you look at the molecule we have on the screen here, what is this? Well, it kind of looks like an enol, doesn't it? It's if you replace the nitrogen with the carbon, it is in fact an enol, and you know that when you see enols, before you can blink, they're going to do proton tautomerization or keto-enol tautomerization to go back to the more stable keto form with the double bond between the carbon and oxygen. So technically this is not an enol, it's an iminol because it's an imine version of an enol, so it's an iminol But that's fine. The mechanism is exactly the same. First, you're going to protonate the nitrogen with its lone pair, and that's going to give you a plus charge on the nitrogen, so that's back to an iminium ion, and that of course is going to want to yank electrons towards the nitrogen. Almost all chemistry of nitrogen-containing compounds can be explained by nitrogen wanting its lone pair of electrons back. So you let the electrons in the carbon-nitrogen double bond resonate, putting the resonance onto the nitrogen with the lone pair being put on the nitrogen there, right? So once you have the lone pair on the nitrogen, that's going to give you, of course, a plus charge on the adjacent carbon. That is going to want to yank on electrons on the, we have two lone pairs of electrons in the oxygen. Just take one of those two lone pairs and let them resonate down onto the plus charge to further stabilize the plus charge by giving us a third place to put the plus charge and stabilize it. And so when we have the oxygen resonate its electrons down, that's going to make an oxonium ion. That oxonium ion is, of course, going to take that proton on the oxygen, which, remember, alcohol protons, pKs of like 16, 17, but now you have a proton on an oxygen that's an oxonium ion, and so the pK of that proton now drops to like down to -2-ish for the pK value. Well, of course, if it's dropping that pK down to -2, that means it's a wicked acidic proton, and any base is going to be able to pull it off. Even a mild base or a weak base will pull off that proton. So the base of this reaction here probably is going to be H2O, but whatever it is, let's say it's a water molecule, it's your general base. It pulls the proton off of the oxygen, returns a pair of electrons to the oxygen, so it gets its second lone pair back, and that produces the succinimide. And the cool thing about this reaction is when you do it, you usually do over the arrow. I didn't say this before, but over the arrow, our solvent is usually something like methylene chloride, so CH2Cl2. Could be methylene chloride, could be chloroform. We used to do it in carbon tet, but we can't buy carbon tet these days anymore because it's highly carcinogenic. We do it in a solvent where the solvent is dense, and so when we put the NBS into the beaker, the NBS is more dense than the solvent, so the NBS sinks to the bottom of the beaker. And you put a stir bar in there, and the solution stirs and stirs and stirs, and then as the reaction proceeds, the bromine comes off the nitrogen, making Br2, and you're left with succinimide, the molecule on the bottom left-hand side of the screen. Succinimide, without the bromine on the nitrogen, is less dense than the solvent, and so it floats to the top. And so it's got a really cool reaction to do, because what happens is, as the reaction proceeds, you'll see is that what looks like is stuck on the bottom is now going to suddenly start to float up to the top of the beaker, and that is the sign that the reaction is proceeding. As long as stuff continues to migrate from the bottom to the top, you know the reaction still is going. Once the stuff has stopped doing the migration, you know the reaction is finished. From there, the molecule generates Br2, and the mechanism for the Br2 bromination is exactly the same as the one you learned in fall quarter. This is just radical halogenation with bromine. I'll show you here quickly on the next slide. That mechanism is here. All right. So you take Br2, you take heat or light. That's going to take this diatomic Br2, which is got this perfect dipole between the two molecules, where there's no preference for the cleavage of the Br2 to have it form a Br plus and a Br minus. So it forms two bromine radicals. It's homolytic cleavage, where that bond splits in half with one electron going onto one bromine on the left, the other electron going onto the bromine on the right. Now, once you have a bromine radical, you'll be in the propagation part of the mechanism. So you're going to have a bromine radical is going to abstract a proton off the backbone of a hydrocarbon. And usually you always want to pull the proton off that would give you the most stable intermediate radical left. Remember, radical rules of stability are exactly the same as carbocation rules of stability, so you always want to make a tertiary radical if you can. If not, then a secondary. And where I normally say never ever make a primary carbocation, you can think about this in terms of radical stabilities are the same, and that tertiary is better than secondary, which is better than primary, but you can in fact draw primary radicals. Don't ever draw primary carbocations, but you can draw primary radicals, as you see on the screen here. This is a primary radical. You wouldn't do a carbocation that way, but you can do the radical that way. So the stability rules are the same, and then of course anytime you can resonance delocalize the radical, that's even better than just stabilizing by hyperconjugation. So you generate your radical here. The radical then reacts with a molecule Br2, abstracting a bromine, which actually puts the bromine onto the molecule to make a product. And in the process of doing that, that generates another Br radical. That bromine radical goes off and finds another hydrocarbon, pulls off a proton, generates a carbon radical. The carbon radical goes after another Br2, makes the product, while at the same time generating another bromine radical, which goes off and finds another hydrocarbon, and so it goes around and around and around in a circle. That's why we call it the propagation phase here of the reaction. And then once you run out of all your bromine Br2, you're completely exhausted all your Br2s, then you get to the termination step. And in the termination step, any two radicals can come together and cap themselves off. So you can have a Br radical and a Br radical. You can have a carbon radical and a carbon radical. Whatever radicals you got floating around the beaker, they come together and make product. That's called the termination step. But in the grand scheme of things, we have so many billions and trillions and gazillions of product molecules that were made, which in this case is this molecule here, that any of these terminated products that you see are so minor that you're not even going to notice them in like an NMR spectrum or an IR spectrum, et cetera, et cetera. Okay, so remember, the whole purpose of the NBS mechanism and reaction is you want to generate Br2, one molecule at a time, at really, really low concentrations. That way, in the presence of an alkene, you will do allylic bromination. Whereas if you have a gazillion molecules of Br2 drop into a beaker, at once, coming out of an eyedropper or a pasture pipette, then instead of doing the radical bromination, you're going to do your bromination you learned in fall quarter, which was just alkene bromination, where you make the trans 1,2 dibromide. So high concentrations will give you the trans 1,2 dibromide on an alkene. Low concentrations will give you the allylic bromination or the benzylic bromination. Okay?